Dubai. So he has completed his PhD from Bardiyar University in the year 2015. So he is mainly focusing his research on photoelectrochemistry, biofuel production from agricultural waste, wastewater remediation, and biomedical applications. So for his credits, he has published more than 68 research papers in international and national journals, and he has written two book chapters and more than 10 conference papers, and he has given 8 invited talks in the international and national meetings and conferences. So with this small introduction, now I request Dr. Bharat Govindan to deliver his talk in this session. Thank you. Dr. Bharat?
Yes, sir.
Yeah. You can share your PPT and start.
Yeah, now you're able to see my PPT?
Yes.
Okay, thank you.
Yeah, you can start now. Thank you.
Yeah, and I congratulate organizer and our organizing committee, especially Vijay Mohan. Thank you so much for inviting me to deliver this lecture, especially this talk. So this talk is very interesting, especially this current ongoing problems, how we encounter these current ongoing problems, because we know, especially even our researchers and then our politicians also continuously speaking about climate change controls. So I'm going to address some of climate change control is very challenging nowadays, especially this era. So how we can help to address some problems, especially related to climate change controls. So here nowadays we are focusing only this type of research. So especially our research mainly focusing on CO2 capture from atmosphere, as well as where the CO2 started from. So we are trying to capture directly, and then we are converting CO2 to fuels. So this is our ultimate research goal. Now we succeed some of research outputs also. So I am going to share with all the things. So this is the overall outline of this plenary talk. So yes, firstly the background, and then technologies for the conversion of CO2 into fuels, and type of current technologies. So what are the current technologies available for CO2 capture and then CO2? So there are few technologies available. Is the catalytic conversion via hydrogenations. So here also I'm discussing about materials and methods. So second technique, catalytic conversion, and then electrochemical conversion, and then photoelectrochemical conversions. So and then summary. So this overall outline of our study, our talk. So in the background, so we should know about what is climate and then what is climate change, and then how we can, what is the main reason. So excuse me. Sorry, this automatic light. So we should know about this climate change, especially in the background. So what is climate change? The climate is the average weather at a given point and a time of year over long period, typically 30 years to 50 years. We accept the weather to change a lot from day to day, but we accept the climate to remain relatively constant. So this is very important. But unfortunately, if the climate does not remain constant, we call it climate change. The key question is, what is the significant change? Where it's change? And this depends upon the underlying level of climate variability. So we should understand, especially crucial to understand difference between climate change and then climate variability. So we should understand these things. So what is climate change? So climate change, just changing the weather pattern compared with compared to last 30 years. So last 30 years we are getting a regular rain pattern, we are getting all regular things, but nowadays they completely changed. Sometimes we are expecting rain, rainy season we are expecting, but we don't get rain. Sometimes we are not expecting anything, but that time, the complete cyclones and so many things we are affecting a lot. And also many like coronavirus, those things, how it's spreading because of this complete climate change only. So that's why the researchers, especially the ongoing researchers, current researchers, they're focusing how to control climate change. So because this is not a one-man person, so we should all overthink about how to control the climate change. So there is main reason climate change. There is two reasons. One is natural reason, and another one is human reason. So in the natural reason, it is very less. So especially variation in isolation, astronomical changes, volcanic eruptions, plate techniques, tectonics, and changes in ocean currents. These are just natural reason. In the natural reason, the climate change is not affecting that much. But in the human reasons, that is very most worstful things. Because of human activities, we produce a lot of greenhouse gases. These greenhouse gases is main causes for climate change. So what are the impact of climate change? So the cost of adapting coastal areas to raising sea levels. So this sea levels raising is very important, crucial thing we should consider. And then relocation of whole towns, shrinking productivity of harvest, prices of basic foodstuffs and consumer goods will rise. Extreme meteorological phenomena will cause widespread poverty. Freshwater, sometimes we don't get freshwater. Sometimes we are getting a lot of cyclone, but we don't cyclone, and then we are getting a lot of water. Okay, whenever we don't want, we are getting a lot of water due to cyclones. And then more wars to gain access to limited resource, loss of the capacity to work due to heat. So these all are the complete, some impact of climate change. Background, so especially, so what is the main reason climate change? That is CO2 emissions. So especially we are using, nowadays we are using petrols and then coals, and then we are producing a lot of electricity from coals, then we are getting a lot of CO2 emission, as well as we are getting, so especially we are producing a lot of other greenhouse gases also. So this CO2 is main reason to completely, climate change. So if you compare last, to now 2010, if you compare 2100, how much due to this climate change, how much is sea level going to increase? Almost 0.8 meters going to increase 2100. So this is the same reason we lost so much our land. So especially we know that this is our, evidence. This is a complete evidence. Why? How this climate change is lost 10,000 years? How much lands we lost already? How much land we are going to lose after 100 years? So if you see the Pumbhar, we know well-known, our Tamil people, we know that Pumbhar is a very old and ancient city, and then a lot of economicals, and then many wealthy cities basically. So this city also now under in the sea. So especially Graham Hancock, he completely, he said completely with so many evidences. He said the complete one of the Pumbhar city is inside sea. Because of why? Because of climate change last 10,000 years, and then we lost so much our historical things also. So even another one example, like one Hindu temple, it is old, 5,000 years old. It's nearly Pali, Indonesia. They found the one complete Hindu statue and the complete Hindu temple is inside the sea. Because of why? This is also one of example for climate change. So and also it not only raises a sea level, and also it is affect some our day-to-day life also. For example, coronavirus. This virus also one of the reason for climate change, and other disease, many disease. Nowadays we are affecting many type of disease. This all because of climate change. So it is very important to control climate change. So what can be done? First, we must admit that climate change is everyone's problem. No agency, government, or individual scientist can fix it for us. We are all in this together. We got there because of our lifestyle, so our lifestyle has to change. What? How we can change? Maybe we should reduce, this CO2 emission by using some common vehicles. So especially because our people are using just every person is using individual vehicles. When we are using individual vehicles, and ultimately we are increasing CO2 level. But when we are just utilizing our common public transport, it may decrease. So we should consider about those things. Then this is a small lifestyle change. We can slightly control CO2, but we can't do. That is a problem. Okay, so this is a problem. So how can we address the CO2 emission? How can we control the CO2 emission? So for this world, it is not possible because we are running a lot of industries and then a lot of vehicles, and for industries also we need coals we should burn, otherwise we cannot get electricity and then run for industries. But it is we cannot avoid the CO2 emission. Then our ultimate aim, how to capture CO2 and then how to utilization of CO2. So this is our basic the current era problems. Then we are also working on this field. So how can we capture CO2 and as well as how can we utilize the CO2 into fuels? So this is our ultimate aim. So this is our ultimate work. So what are the technologies available for CO2 conversion into fuels? So what are the technologies? How the people are using some technologies to CO2 converting CO2 into fuels. The available technologies: reforming, electrochemical, and biological, and photocatalysis, and then photoelectrochemical studies. That is very advanced field. In the reforming, there is two techniques: plasma reforming and then thermal reforming. In the plasma reforming, what we need, some materials we need, like hydrogenation. The technique is hydrogenation, and then we need some materials like nanocatalyst or other porous materials. And then we need, especially we need bioreactors to conduct this experiment. Actually, this research all are in the lab scale only, but based on this lab scale research, we are going to implement this for commercial purpose. So especially we can directly capture CO2 and then conversion of CO2 into fuels. And then in the electrochemical also, we need electrode materials, and then these techniques are very good. And then this is very rapid conversion technology. And in the biological also, required biocatalyst, required very specific conditions, specific bioreactors, short lifetime of biocatalyst. So actually every technique is having some merits and then demerits. So I may explain later what are the merits and what are the demerits. In the photocatalyst also, we need more materials, and then this is somewhat economical process, and then required normal temperature and pressure, sustainable process, and then high stability of catalyst. So if you see here, we have two techniques. So from here we have two techniques. One is electrochemical and another one is photocatalysis. So in the electrochemical, rapid conversion technology, this is the main advantages for electrochemical. And then photocatalyst, high stability catalyst, this is an economical process, and then required normal temperature and pressure compared than reforming. So reforming, somewhat it is not adorable technology for the CO2 conversion, but when we combine this both technology, okay, electrochemistry, then this is the best technology for conversion of CO2 into fuels. So I may explain about detailing. So what are the catalysts required? So the catalyst, homogeneous catalyst, biocatalyst, and then heterogeneous catalyst. In the homogeneous catalyst, importantly, we need acid-base catalyst and then transition metal compounds. In the biocatalyst, including enzyme and embolies enzymes and cells. And then heterogeneous catalyst, bulk catalyst, and supported catalyst. So especially in the supported catalyst like metal carbides, metal nitrates, metal oxides, and then metal sulfides. So if you see in the heterogeneous catalyst, this heterogeneous catalyst always give the best performance compared than homogeneous catalyst. So people are always using, why the people are always using, nano composite material. In the nano composite materials, especially nano hybrids, they are getting acid base catalyst as well as metal hydride base. So these both properties very important to convert CO2 into fuels. So that's why people are always designing heterogeneous catalyst for CO2 conversion. So I already explained conversion techniques. First thermal reforming, and then electrochemical conversion of CO2, photocatalytic conversion of CO2, and then electrochemical conversion of CO2. So first, this thermal reforming. In the thermal reforming, this is the simple objective. So we have, so this is the reactor. This is a reactor. So we have here ligands, additive, and precursors. So when we just pass hydrogen gas and then CO2 to this reactor, this reactor we already use some catalyst. This catalyst is easily break CO2 bond, and then it is directly converted to methanol. This is one type, and then another one type, and then catalyst, and then second maybe some people are using ruthenium based catalyst, because ruthenium based catalyst is a very stable catalyst for conversion of CO2 into methanol, because methanol is also one of the fuel. So in the third type, so what are the types available for thermal reforming? So one, gas phase reactor, and another one is liquid phase reactor, and another one is final one, gas liquid phase reactor. People normally using this catalyst, liquid phase reactor. This liquid phase reactor, we need solvent and then catalyst. These are all catalyst, and then we just supply CO2 and then H2, and then we can get, and after the reaction we are getting CHO4, CH3OH, and then COOH. These are the hydrogenated products. So this paper recently we published, because we used a liquid phase reactor. From this liquid phase reactor, we successfully converted CO2 into CH3OH. So in this paper, so especially this is our one of research articles and recently published. So in this article, we used hybrid palladium, ruthenium, and then magazine nanocomposite. We know that magazine is perfect acid base substrate. This may help to rearrange of carbon and oxygen bond also. And then this palladium and ruthenium is metal catalyst. This metal catalyst help to break carbon and then oxygen bond and then insert hydrogen. So this is the main reason why we are selecting this material. So this material, we successfully converted CO2 into CH3OH. So this is the synthesis mechanism. We used commercial magazine, and then we converted magazine nanoseed, and then we used FISPEM DNA, because FISPEM DNA is a ligand. So it is very easy when we are functionalizing this FISPEM DNA. It gives the anchoring site. Just wait. Anchoring site for metal nanoparticles. So here our metal nanoparticle is palladium and ruthenium. So once we functionalize this FDNA in the magazine, and then after that, especially palladium and then ruthenium chloride, we took this for as reactant, and then we successfully converted these palladium and ruthenium ions to palladium ruthenium using sodium borohydride. So especially sodium borohydride is very strong reducing agent. We used this study for converting palladium ions to palladium nanoparticles. So this main thing. So these are flexible mechanisms. And then this one is FSM and then DEM morphologies. So if you find this is complete one. So this is a magazine seed, and then our nanoparticles are deposited here. So this is a completely palladium ruthenium nanoparticles. We confirmed through XID and other characterizations, and also here we presented SAD for confirmations. So this is the complete catalytic CO2 reduction, how our material can convert CO2 into fuels. So here we developed integrated system like ethylene glycol. So if you see ethylene glycol and then H2O, this is the best capturing solvents. It easily captures CO2. When we pass CO2 to this, chamber, so this is a hydrogenation chamber. When we pass this CO2, then this CO2 is easily captured ethylene glycol, and then already our materials, we dispersed our material in the solvent. Our materials also inside, and then CO2 molecules also inside the ethylene glycol and then H2O. This is the complete solvent, and here. The best advantage, we use the sodium borohydride as hydrogen source. So if you see here, so we performed this is 120 degree and then 12 hours. This is a complete reaction time, because this is a very low reaction temperature. We can convert CO2 into methanol, CH3OH. So this is the complete things. When we add, this is the first step. When we add sodium borohydride, and then it is produces hydrogen. This hydrogen is, see, this is our titanium. This is a titanium carbide. That is magazine seed, and this is our material. And then when we dissolve sodium borohydride, it is produces hydrogen, in situ hydrogen. Then this hydrogen is easily bond with this metal. Then it is formed metal hydride. And then you have also CO2. This CO2 is easily attached with near to this titanium carbide, and then especially this step, this metal hydride easily break this carbon O bond and then insert hydrogen. So this is main aim. So here this titanium carbide capture CO2. It is capture CO2, and then this metal hydride, actually palladium ruthenium hydrogen. This metal hydride easily react with the carbon CO2 and then break CO bond and then insert H bond. Then we finally get, so this every reaction we finally get CH3OH, from CO2 to CH3OH. This is the final step. So we completely presented this reaction based on our experimental conditions. So if you see here, so especially in this hydrogenation, so this first graph is a hydrogenation. When we are using pure magazine, palladium ruthenium and magazine. This palladium ruthenium and magazine giving the maximum conversion, because this is a conversion, and then this is yield. So it is giving CH3 methanol yield more compared than other two catalysts. And also we optimized some conditions, so especially ethylene glycol and water, because ethylene glycol and water is very important, because for electrolysis, for sodium borohydride electrolysis, water very important. But if you add more water, then it lead to formation of formic acid. So we need our selective product is CO2 to methanol. So for this, we should optimize the condition. We optimized this 18.2, 18% ethylene glycol and then 2% water. This is the best solvent to capture CO2 and then conversion of CO2 into methanol. So this, and also time, we found the time also. So especially this 12 hours, we can almost we reach 18%, 70% yield CH3OH, and then 75% CO2 conversions. And this is a turnover number. We are obtaining maximum turnover number per hour. So this is our, the complete research, and then we successfully converted the CO2 into fuel, especially methanol. But this, especially we need high reactor for this reaction, and then temperature and time also, almost 12 hours. So this is somewhat a little disadvantages, having some disadvantages. For this purpose, the people are looking for alternatives, so especially electrochemical conversion of CO2. So how they are doing electrochemistry for conversion of CO2? Here we know that in the electrochemistry there is anode and then cathode. So in this anode they supply in the anode, so we need electrolyte. We need complete electrolyte. So when we pass the CO2, this CO2 goes inside, and then it is dissolved in electrolyte, and then it is contact with the surface of cathode, and then it is convert CO2 into CH3OH and then other molecules. So this is a complete techniques. Explain this here. So this is electrochemical conversion, the techniques. This is electrochemical cell. So we having this is working electrode compartment, and this is especially this is anode part, this is cathode part. So here also we can use here counter electrode. This is our working electrode in the cathode part. Reference electrode we already insert in the reference electrode, and then we have two compartment system. So one is anode part, and then another one is cathode part. When you supply the CO2 to cathode side, and then it is reduced on the cathode surface, and then it is produced carbon monoxide, CH3OH, and then formic acid, so many things. Okay, so this is also one type of techniques, conversion techniques, CO2 into fuels. So this is a complete mechanism, how it's work. So we applying some potential through cathode and then anode. So here the CO2 react with cathode, and then it is produced CH3OH plus H2OH. How? Because CO2 conversion, when the CO2 molecules turn to CH3OH, we need 6 electrons and then 6 protons. These 6 electrons we can get from when we are applying some power, we can get these 6 electrons, and then how we are getting 6 protons? When we are doing this experiment, so in the anode part, H2O is reactant. This H2O oxidize, and then it is produced O2 gas, oxygen gas, as well as 6 protons. These 6 protons easily transfer through this membrane. This is a proton exchange membrane. It is allow only protons, and then these 6 plus ions, these protons reach to this chamber, cathodic chamber. Already 6 electron is there, CO2 molecules also there. Therefore CO2 molecules react with the 6 electrons and then 6 protons, and then it is converted to CH3OH. Okay, this is the main electrochemical conversion techniques. So if you see here, so especially how this electrochemistry, how it's work. So this is the complete mechanism. So how CO2 to CH3OH, how it's formed. For example, how CO2 format ion forms. When CO2 molecules react with 1 electrons and then 1 protons, then it's formed format ions. Again, these format ions again react with 1 proton, 1 electron to form formic acid. Again, this formic acid react with electrons and then 1 protons, and then to form HCO plus H2O. Again, it's react with to 1 electron, 1 proton, forming CH2O, and then again react with 2 electrons and 2 protons. It's to form CH3OH. This is the complete overall mechanism, how CO2 split, sorry, how CO2 reduced into CH3OH. Okay, so this is the thing. Okay, so when we converting CO2 into when we are doing conversion, we are not only getting CH3OH, other product like CH3OH, and then H2 also, and then methanol, and then formic acid, and then this carbon monoxide. Okay, we are getting all type 1, 2, 3, 4, 5, 6, 7 type of products, reduced products we are getting every potential. This is potential, recovered potential. So especially here we should understand each and every potential we are getting different type of CH3OH. So it is purely based on your electrode materials. So these are also one of type techniques. So this is electrochemical conversion techniques. So the people are successfully converted these electrochemical CO2 into fuels by using these electrochemical techniques. And then another technique is photocatalytic conversion. So we actually, our people knows clearly how this photocatalytic system working, because we normally we classified materials like conductor, semiconductor, and then insulator. In the most of the time we are using the semiconducting material, because semiconductor materials only having band gap. When we are passing some lights, especially these valence band electrons are getting excited, then it's transferred to conduction band. Their holes produce. These holes react with water to produce O2 and then H plus ions, and then again these these conduction band electrons react with the CO2 molecules, and then it is produced CH4 and then CO. So this is also another one technique. But so this is in the techniques. Even our Indian people also, some peoples are working. So these are two. Here also the people made two techniques. One is a solid liquid mode, and then solid vapor mode. Okay, so in the solid liquid mode, here we catalyst and then H2O. H2O is absolutely, that is reactant. Even here we can use ethylene glycol and then H2O mixer also, because ethylene glycol we already found this is best solvent to capture CO2. And then when we using this H2O during this H2O, because this H2O split O2 and then plus H plus ions, protons. These protons very needed, very important for converting CO2 into CH3OH and other molecules. When we pass our sunlight to the material, the semiconducting material produce a lot of photoexcited electrons. These photoexcited electrons, and then during the oxidation also happen. This also oxidation also H plus. This also involved to convert CO2 into CH3OH. This is normal photocatalytic system. So this photocatalytic system, and these are the two techniques. So people are normally focusing, this is all in liquid mode, because this is very conventional mode. And then this is also very easy way to mode to converting CO2 into fuels. And then this is a complete reactor. So if anyone want to set up this reactor to your lab, you may consider, because we need lamp. So the complete lamp, so 3-side lamp, and then this is 3-necked flask, and then this is CO2 supply. So if you supply CO2, here you found your solvent as well as your materials, then you supply your CO2 here, and then give some time to observe your CO2 into solvents. Okay, give some time like 60 minutes, even 120 minutes, and then when the CO2 molecules is captured by your solvent, then you may start your reaction, and then pass some light. This light directly react with your this is mechanism, complete mechanism. So this is individual nanoparticles. When you are passing your photon light, these valence band electrons are excited to conduction band. This is conduction band electrons. This is holes. These holes react with water and to lead for oxidation of water and lead for O2 production, the oxygen production. Sorry. And then these photo excited electrons especially and then react with CO2 molecules to produce CH4OH. This is complete setup. And then whenever in the every time, so if you see this 6 every time maybe 30 minutes, 60 minutes, and then 90 minutes, you can just take the sample away and then do GCMS, because the GCMS, this is a gas chromatography mass spectrometer, and then HPLC. From this, you can estimate how much CH3OH produced during this time. Okay, and then this is the complete mechanism how the CO2 converted into CH3OH by using different photocatalysts. The people normally use TiO2 and then carbon-based TiO2 because that material is very good. And then it is also, when we combine with the TiO2 and other plasmonic materials, then we can get the wide visible up to visible range. So we can easily convert CO2 into CH3OH. This is the complete the working formula. So how this TiO2 especially involved to form how involved to converting CO2 into CH3OH. So this is all basics, because we know how previously dye degradation techniques. This is also based on the dye degradation techniques. Here instead of dye degradation, here we are using CO2 to convert CO2 to convert CH3OH. This is the main. So this is the overall overall formula. So how this CO2 converting into CH3OH and by using this photocatalyst. So these all are some suggested core materials. So these core materials so these all are the band gap and then potential vessels also. So if you want to convert the CO2 and then CH4, you need a minimum minus 0.2 volt, 24 volt. Then you may decide your material according that. So this is very important. When you go for some hybrid material, the properties also can change. Even the size, so especially why we are using nanomaterials, because our nanomaterials giving different size of material, different size of material giving the different band gap. For example, higher particle size giving lower band gap, and the lower size of particles, nanoparticles giving higher band gap, like quantum dots. So if you just design what material you have to work based on your theme of study. So I explained this photo. I explained already electrochemical and then photo techniques for conversion of CO2. Now I'm explaining about photo electrochemical technique. This is the last techniques. So if you see here, here also we are using. So especially we are using photocatalyst. Okay, this photocatalyst as photo anode or photo cathode material. So normally for electrochemical conversion we need electrode. That electrode material should be photoactive material, means that is photoelectrodes. That's it. Okay, simple. So especially suppose I'm going to use just ruthenium modified nickel foam or ruthenium modified any electrode, that may be pure electrochemical electrodes. But when I'm going to use TiO2 based material for electrochemical application, that is called photocatalyst. Just we are using instead of metal, we are using some semiconducting metal oxide nanoparticles for fabricating the electrodes. That is called photocatalyst. Simple. Okay. So here we are using photocatalyst as photoanode or photocathode. When we apply small potential, and the same time when we apply some light energy, okay, then it is immediately, actually very rapid time, it produces a lot of electrons and then protons. Okay, so these electrons, a lot of photo excited electrons and then protons also produce another side. This will immediately convert CO2 into fuels. So this is what we are using. This is what we are combining these both techniques, like photochemistry and then electrochemistry. Then we combine this photo electrochemistry. Okay, so this is the complete techniques. So we recently published one of paper with our Korean friends, and then we successfully prepared TiO2 incorporating with the plasmonic nanoparticles. So in the TiO2, especially TiO2, it is batting up like UV range. But when we incorporate with silver nanoparticles, so especially silver nanoparticles, it is visible light active. Okay. Then when we combine this both material, this Ag act as electron scavenger, and then as well as it is also produces some hot electrons. So electron scavengers. So why we are using this TiO2? Because we already know TiO2 having valence band and then convex band. When we apply some potential, then it is produced photoelectrons. When we supply some potential, and then it is give more electrons, and then it is also give photoelectrons. Okay, then n number of electrons available one side, and another side, during water oxidation, it is producing enormous H plus ions. So these protons easily react, go through membrane exchange, and then it is reached to the cathodic chamber, and then already we have enormous electrons in the anodic or cathodic chamber. And then these protons also reach, because of water splitting, the lot of protons are produced through another chamber, and then it reached to the CO2 reduction chamber, and then it is converted a lot of CO2 molecules into CH3OH. So for the reason we using especially this TiO2 and then plasmonic nanoparticles. So in this hybrid structure, this Ag nanoparticles as electron scavenger, as well as it is producing a lot of hot electrons. So more number of electrons is very important to converting CO2 into methanol. This is very advanced field. So this is our techniques of how we prepared these materials. So we have already GO, and then we apply some Ta4 plus, and then this is NaOH. We converted titanium hydroxide. This titanium hydroxide 140 degree for 6 hours. In the hydrothermal, it is produced as TiO2. Okay, this is the first step. This is a TiO2 RGO nanocomposite. And after that, we took mangrove leaves. This mangrove leaf extract is easily converted Ag plus to Ag 2 plus 2 Ag not nuclei. This Ag not nuclei is attached, mixed with this titanium and then RGO. This Ag also formed near to the TiO2, and then after microwave process, we obtained Ag TiO2 RGO nanocomposite. So this is this hybrid, and then this is pure TiO2 and then RGO nanocomposite, and then this is a pure TiO2, and then this is RGO, this is a TiO2, and then these nanoparticles are Ag. So we confirmed from this, the high resolution spectrum, we confirmed that we successfully formed this TiO2 and then Ag nanoparticles on the surfaces of RGO. Okay, this for photocathodic material for converting CO2 into fuels. Okay, once we prepare this material, how can we, how can we fabricate the electrodes? So this is the cell, the complete cell, photoelectrochemical cell. So here, this is a cathodic part, this is the anodic part. This anodic part, this is water splitting, like H2O, water splitting. It is produced, during the water splitting, it is produced O2 and then H plus ion. This H plus ions easily migrate here. Here we fix proton exchange membrane. This proton exchange membrane only allow protons. So H plus ions easily pass through this membrane, and then it is reached to this chamber. This is CO2 reduction chamber. This is photocathode. This photocathode, we apply some sunlight. Okay, apply some sunlight, then it is produce electrons, and then we also supply some electrons. So here enormous electrons are available this side, and also H plus ions also reached this chamber. And then when we supply CO2, this CO2 go through this electrolyte, then this CO2 convert into CH3OH. Okay, so in this electrode fabrication, so we need this is just for example. So this is your active material, and then use some carbon black or some binding agent, then mix it and then make it like ink, and then you just just spray or print. Then you can get the complete electrode. This complete electrode you can place as your working electrode. That's it. So this is a photo electrode. Suppose the people are here, people are used for platinum carbon. Okay, this is electrocatalyst material. But if you use like molybdenum sulfide, WO3, and then TiO2, and then base photocatalyst, this material, this electrode like photo electrode material, electrodes. That's it. Okay, simple. And then this is potential state. So once you prepare your electrode, so you should characterize your you should characterize the electrochemistry. So this is our working electrode. When we pass our light, this light produces some this electrode produces some for current also. Okay, that current means it is produced a lot of lot of electrons. And then it is produced H plus ions. That's it. Okay, the CO2 is reduced in this chamber. Okay, so how you characterize it? So this is one best techniques, linear sweep voltammetry. Linear sweep voltammetry. Therefore, you can use this linear sweep voltammetry for characterizing your material. So first one is pure TiO2 tar. It is giving very less current density. When you TiO2, you run TiO2 and then R2O, it is also give some noticeable current density. When you just presence of light, it is give the current density compared than target, giving more current density. So more current density means it is photo electrochemically active material, this KGTiO2 R2O. When we supply CO2, then it is giving more current density, So that means when the current density is more, then it is more number of electrons are involved to conversion of CO2. Okay, so this is also another one techniques, the complete techniques. This is EAS. So based on the resistivity, we can find the dark and then on conditions. But when we place actually this is 3 electrode channel. We are not completely utilizing our produced electrons. But when you use that chamber like the 2 electrode chamber, then all photoelectrons are used, and then we may easily convert CO2 into fuels. This is another one technique. So from this techniques. Okay, so from this photocatalyst, especially this is a TiO2 and then R2O, this is a Ag TiO2 R2O, we obtained the yield CH3OH. This is blue color CH3OH. We obtained more yield compared than TiO2 R2O. Therefore, here especially this Ag nanoparticles purely working, because I already explained these Ag nanoparticles also visibly active, and it is also produce active electrons, and then it is electron scavenger. When we pass light, sometime the excited electrons again it's come to the valence band. This is called a recombination effect. So when you use some metal nanoparticles like silver and other metal oxide nanoparticles, we can just remove this recombination effect. So if you remove the recombination effect, means you can get more electrons, therefore you can get more conversion performance compared than CO2 into CH3OH or other molecules. Okay, so Especially this is our working setup. So this is our TiO2, AG incorporated TiO2 RGO, and then we use the platinum as anode material. So when we apply some potential, then during the water splitting, we can get H plus and then O2. This H plus is easily migrate to the other side of photocathode. Then this H plus and then E minus when we supply line. It produces a lot of electrons. It produces a lot of electrons. These electrons and then already protons are there in the chamber. These both react with the CO2 molecules and then it is produced CHO4, CH3OH, CO. So why these all? Especially these are CO, formic acid, CH3OH, ethanol, CH4, this hydrogen. These are competitive, reduction compounds. Why we are getting this much? Because sometimes we are not controlling the complete electrons. Therefore, it is react with the CO2 molecules into other like formic acid, CO, and then CHO4. But here, our target aim to produce CH3OH from CO2. Therefore, we optimized our condition based on the based on the CHO3 formations. So, if you find here. So especially, so this is the complete working principle. In the cathode, we have AG and then DiO2 and then H nu. And this AG also produces hot electrons, and then TiO2 also produced conduction band electrons, and then H plus. Okay, holes. These holes, this is cathode side. These holes react with water. Okay, and then it produces 4 OH plus ions. This cathode side. Here we used this photocathode as reacting materials. Okay, photocathode as CO2 conversion, and then anode as to produce 4H plus. Okay, so in the cathode also we produced hot electrons and conduction band electrons, because hot electrons from AG, conduction electrons from TiO2 when we apply some potential. Okay, and then in the anode side we produced 4H plus and then O2. Okay, during through water splitting, and then these 4H plus ions react with your electrons, your hot electrons and the conduction band electrons to produce this different compounds. So especially, for example, 2H plus electrons, 2 proton, 2 electron plus CO2 produce carbon monoxide plus H2O. Same, this 2H plus again 2 electrons and then CO2. This also produced HCOH, and then for the CH3OH formation, this is methanol formation, we need 6H plus and then 6 E minus. E minus means 6 protons and then 6 electrons we need, converting CO2 into CH3OH. In the same, if you want to methane formation, so 8H plus and then 8 E minus we need. And also the ethanol formation you need 12 protons and then 12 electrons, and sometimes we are getting hydrogen production also through this cathode. So these materials are depending based on the your materials. So what type of material you are designing. So here there is so many research problems are there. Okay, so how can suppose you want to convert CO2 into carbon monoxide. Okay, so you need just 2H plus and then 2 electron minus. So you need just minimum energy, minimum current, and then maximum current. Okay, so it is completely based on your material, whatever material you are designing. It is based on your band gap, based on current density, how much you are applying potential. Okay, then based on that you can optimize your selectivity or yield of the products. Okay, this is you can find many research problems from this here. Oh, this is also some suggested materials. So like Fe2O3, WO3, MOS2, TiO2, copper, and then copper Indium sulfide. So these all are the different materials. So you can use this material because this is also different band gap. So different band gap produce a different conduction band electrons. These different conduction band electrons react with the CO2 molecules to produce a different type of compounds, reducing compounds like methanol, ethanol, CO, and then CH4, extra. Okay, and then the people recently they using integrated system. The integrated system is this is a complete CO2 capture and then CO2 conversion. Actually, this is a typical system for future. Okay, when we just directly capture from industry the CO2, this is flue gas from flue gas. We are directly capturing from the industry. Then we just send this to one high temperature fuel cell. This is also a CO2 capturing system. And then once it is once our solvent is capturing the salt, then we can send this solvent with the CO2. The complete captured system to that electrolyzer. This electrolyzer is completely convert CO2 into fuel. Then we can collect this fuel. Then we can collect this fuel, and then meanwhile again we can supply this. Here CO2 molecules is high. Then here we converted everything, and then here also pure without free CO2 surfactant. Sorry, what you call the solvents. Okay, this solvent again pass through this chamber, and then this is a recycle. Okay, this solvent is just capturing CO2 and then just supplied to the electrode surface. This electrode surface is easily converted CO2 into CH3O4, and then again the CO2 free this solvent again pass through this chamber. Okay, this is a complete recycle chamber. So maybe in the future, maybe this is the typical techniques integrated system, CO2 capture as well as CO2 conversion techniques. Actually, this is not available right now. So this is our our research output maybe in the future. So in the summary, we came to summary. The conversion of carbon dioxide. So here also we having I explained the reforming. Two techniques, plasma and then thermal reforming. I explained one of our research articles, so related to how we converted CO2 into fuels by using sodium borate and extra for hydrogen source. And then electrochemistry, I explained electrochemistry and then photoelectrochemistry, and then finally I explained photocatalysis, and then finally I explained photoelectrochemistry. So these are our things. And in the before conclusion, especially we are very sad about Vivek sir, because he is the genius, because CO2 conversion, especially CO2 emission, how we can control CO2 emission only planting the tree. Okay, so he organized one green club organization, and then he almost 30 lakhs to 40 lakhs trees he already planted by using several sources, especially peoples. And then actually he did a lot of good things to our environment, because only CO2 utilizing thing is plant, because for photosynthesis CO2 very important. So more number of the plants typically reduce CO2 from our atmosphere, and then it is prevent climate change. So for this, actually we really miss this person. So I really, especially this talk, I just take it to Dr. Vivek sir. We really miss this fellow for especially for this planting, etc. And also he is a very good person personally also. So I thank his activities also, social activities also recently. And thank you, Vivek sir. I just dedicate this talk to you for your and then may your soul interest in peace. And thank you so much. And then if any questions, then please proceed. Ask.
Yeah. Thank you, Dr. Bharat Govindan. It's my pleasure to thank you on behalf of ICECS team and as well as the audience. I hope audience got a lot of information from your talk, and now the session is open for discussion. audience can either unmute themselves and talk, means ask their questions, or you can also chat in the chat box. So meantime, I can ask my questions. I have like few things. Uh,
Yeah.
yeah, first one is about this choice of palladium and ruthenium. Why you have chosen palladium and ruthenium? Like I was means I'm talking about the first part of your talk, that
Yes, yes.
palladium ruthenium amexin composite catalyst. So why palladium, ruthenium? Why not other noble metals like platinum? And what about other transition metal based catalyst? Uh,
Yes, actually, why I'm using palladium and ruthenium? Because if we are going to use pure palladium as metal nanoparticles, then it may lead to high cost. But when I'm using some transition metals like nickel, cobalt, and then other metals, when we are going for high reaction temperature, then it is get easily oxidized. So I need to reduce the cost of the material as well as I need higher stability of the materials. So that's why I just go prepared ruthenium and then palladium nano particles for decorating materials. So these materials highly very active for dissociation of hydrogen, because hydrogen insert is very important when we are taking CO2 bond, C double bond O2, okay, bond, okay. Therefore, even compared than pure palladium, this palladium ruthenium giving the best property, so best hydrogen dissociation property, then it is actually convert metal hydride. This metal hydride is beneficial for converting CO2 to other molecules, okay.
so
So that's
basically,
why,
ruthenium is activating palladium, right? Uh,
yeah, actually, ruthenium is also one type of active
Catalyst.
materials only. But when we combine these both metals, palladium and ruthenium, it giving more active surfaces compared than pure metals. So that's why our ultimate aim to increase the performance as well as reduce the cost. So that's why we
And one
took
more
this
thing is
palladium
about,
and ruthenium.
yeah, one more thing is about the phase of these palladium ruthenium catalysts. Are they forming alloys, or they are like phase separated?
No, it is alloy. So actually, it is very like 6 to 7 nanometer particles.
Okay.
Individual, it is completely mixed with alloys, but we don't have the complete details of the alloy where the ruthenium and then palladium atoms are attached in the HCP structure. So that is a hexagonal structure. Actually, FCC and the HCP both we obtained. So we don't have the exact structure because we need more sophisticated instruments. We need to characterize those things where the palladium and then ruthenium attached, especially synchrotron radiation. We need we don't have that much facilities here, so we use as usual. Yeah.
Okay. Thank you for your explanation.
Thank
Now I
you.
will wait for audience question. Maybe I can wait for a few minutes.
Yeah. Okay.
You can even chat it in the chat box.
Yeah, we'll check.
If you are
Mm.
comfortable in asking Tamil, so you can also use. You can just directly ask things in Tamil.
Yeah, in the chart, I don't find any questions.
Yeah, in
Okay.
chat actually there is no question, but
Yeah. So,
if there are no questions, let's thank Dr. Bharat Govindan again. Thank you so much for your informative talk, and personally as well as on behalf of audience, we again thank you for your research on climate change problems. It's really
yeah.
timely and very important for our life in Earth. Thank you so much.
Thank you. Actually, I am wishing also to our researchers to focus more climate change based research. This may be helpful to keep our earth green. Thank you.
Yes,
Thank you so much, our
yes. Thank you so
researchers.
much.
Thank you.
Thank you, Dr. Bharat.
Yeah, thank you,
Thank you very much
Mohammed,
for
for
your
your
valuable time with us, spending with us.
I congratulate your
Thank you.
organizations. Thank you.
Thank you, sir. Thank you. Thank you, Dr. Karthikeyan. Dr. JK.
Thank you, Morgan. Yes, thank you.
Yeah, thank you for chair this session. Thank you very much. Participants are requested to fill the feedback forms as soon as possible. The next session will start on 2 o'clock. Please join 10 minutes before. Thank you. Thank you very much.